All right, Ivan, can you hear me okay?
Yes.
Awesome. All right, let's get started. So hello, good morning, everybody. I hope you're having a good week. Couple quick announcements. We have our chapter 4 quiz next week, and that is going to be on Tuesday. On the syllabus, it was originally scheduled for Monday, but Monday is a holiday, which I failed to notice when I first scheduled it. But a few weeks ago, I changed the date on Moodle. So in case you hadn't noticed that date change, our chapter 4 quiz will be on Tuesday, which just means you need to find a 1 hour period to submit your chapter 4 quiz. Let's see what else. In addition to that, we are just sort of finishing up our chapter 4 work this week. There's 3 applications that we're going to be working through. Today, we're going to do the business and economic applications. And then on Thursday, we'll do biology and chemistry applications. And so today's lecture is a little bit short. It's intentionally shorter than a full lecture because when we do the business applications, it sort of predicates that you also bring in and remember all of the other economic units that we've done. So in chapter 1, it was 1.4, and in chapter 2, it's 2.5. So we'll have to be using that information as well in this section, which is 4.4, as well as the stuff we've learned about things like critical points and maximums and minimums. So you will need a little time to go back and review those in order to do the homework and to do the quiz. So today's lecture will end a little bit early so that you have time built in that you could do that if you wanted to. Other than that, I think that's it for announcements. I'm going to go ahead and switch over to the doc cam. Okay. And so we're briefly just going to go through what we learned in chapter 1 and chapter 2, sort of the main points, so that we can then move on and talk about this in the context of chapter 4. So this is chapter 1 stuff. This is chapter 2 stuff. So let's talk about that for a moment. So just as a reminder, our cost function, we use C of Q, and that is from a producer or seller's perspective. So it's the amount of money it takes to produce your product, so to make it. So how much does it cost you to make your product? Within that, we have something called fixed cost, which is the cost to produce 0 quantity. And so that's the cost before you've made any items. So this will commonly include things like if you bought a machine or a building, but you haven't actually made anything yet, those are sort of upfront costs, which we call fixed costs. Then we have revenue, which is R of Q. And revenue is the amount of money taken in from selling a product. So you've made whatever it is that you're going to sell, and then you go to sell it. Revenue by default is price times quantity unless you are told otherwise. So P we use for price, Q is for quantity. In general, price P is a constant, so it's a number, and then Q is the independent variable. We'll see an example later where revenue is a little bit more fluid, but in general, this is, price times quantity. Price is what you're selling it for. And then profit, right? We use pi of Q, and profit's the amount of money you make by producing and then selling the item. So it's revenue minus cost. And so that order is important. It's always revenue minus cost, and that will tell us how much profit we're making. So that's back from chapter 1. And then in chapter 2, we said, okay, marginal cost is the derivative of the cost function, and marginal cost is the additional cost to produce one more item. Marginal revenue is the derivative of revenue, and marginal revenue is the additional revenue from selling one more item. Marginal profit is the derivative of profit, and marginal profit is the additional profit from making and selling one more item. So that was what we did in chapter 2. We talked about looking at that and doing some assessments. So what we're going to do is we're going to start with just sort of a very typical problem here, which is going to bring in some stuff from chapter 1, some stuff from chapter 4. So here, suppose the cost to produce an item is given by C of Q equals 10Q squared plus 1400, and revenue is given by 4400 Q. So part A, how much does it cost to make 15 items? Part B, how much does each item cost when they are for sale? So be careful with the wording of that one. So those 2 questions go back to chapter 1 and just understanding how these functions work. Part C, what is the profit function for this model? So we're just setting it up using the definition. And then parts D and E. What is the quantity that maximizes profit and what is the maximum profit that can be achieved? So D and E, we're now talking about maximums. So this is bringing in what we learned in 4.1 and 4.3 about maximums. So think about what we would do for other functions if we were looking for a maximum. So you really need to do part C and set up an equation to be maximized before you can do parts D and E. And D and E are looking for two different things. So we want to really make sure we're reading the question carefully and answering it with the correct number because there's two numbers sort of associated. So I want you to try this out. There's 5 parts. I'll give you about 4 minutes to do them. See what you can do, set it up. Feel free to look back in your notes from earlier chapters on this or even back to the early stuff on chapter 4, but try it out. And then in about 4 minutes, we'll go through it together. Okay, take about 30 more seconds. All right. So for part A, how much does it cost to make 15 items? 15 items is a quantity, and we're talking about the cost function because how much does it cost to make? That's the same thing as produce 15 items. So we're going to go ahead and plug in Q equals 15 into the cost function. So we have 10 times 15 squared plus 1400. We're going to crunch that number and we're going to get $3,650. So as a reminder, the cost, revenue, and profit all have units of dollars because we're talking about money and currency. So this is directly related to the cost function. Okay, so that's back from chapter 1. For part B, the wording on this is a little tricky. So it says, how much does each item cost when they are for sale? So we see this word cost, and you may think cost function, but we're talking about actually the price, right? So this is a sort of sneaky way to ask about the price. What is the price of an item when they are for sale? So if we're talking about when something is for sale, we're talking about revenue, right? That's when we're selling our item. So the cost of the item, which is the price, is the constant in the revenue equation. So we are selling these for $4,400, and that is the cost to the buyer. So don't get super tripped up on the fact that it says cost. You really just have to sort of think about what the question's asking, excuse me, and use the correct equation accordingly. Okay, so that one's a little tricky with the wording because it does say cost, but we're really talking about the price here. Okay, so now part C, what is the profit function for this model? So as a reminder, profit is revenue minus cost, right? We have that up here, revenue minus cost. So we want to fill in the actual functions. So revenue is 4,400Q minus cost. So for subtracting off the cost equation, we're subtracting off 10Q squared plus 1400. And as a reminder, you're subtracting off the entire cost function. So you either need to use parentheses or make sure the minus has been distributed to both terms. Okay, so we've set up the profit function, and that setup is what's going to allow us to answer parts D and E. So part D says, what is the quantity that maximizes profit? Okay, so we're looking for quantity, we're looking for Q, and we want to maximize profit. So we want to maximize this function, and our solution should be Q equals something. So remember, when we're looking for maximums, the first thing we think of is critical points. We don't have any bounds here, so we're looking for a local maximum instead of a global maximum, although this could also be a global maximum depending on if there's only one critical point. Okay, so when we take the derivative here, we take the derivative of each term. The derivative of 4,400Q is 4,400 minus, now the derivative of 10Q squared, 20Q. The derivative of 1,400 is 0. So now we want to know, when does that equal 0? Right? That's how we find our critical points. So if we bring 20Q over and divide, we get Q equals 220. So we have one critical point, okay? And we have to make sure that it is actually a maximum. Because imagine that you're a business person and you find a critical point and you say, hey, this maximizes profit, but you didn't check and you accidentally minimize profit. That would be really bad, right? So how do we make sure that this is a maximum? Let's use the second derivative test. I think will be the easiest here. The second derivative of profit, the derivative of 4,400 is 0. The derivative of negative 20Q is negative 20. And so our second derivative test says if your second derivative is negative at your critical point, so this is negative everywhere, the original function's concave down, so it is a maximum. So if the original function is concave down everywhere, not only is it a local maximum, it's a global maximum. Okay, so we maximize profit when quantity is 220. So that is the quantity that maximizes profit. Part E says, what is the maximum profit that can be achieved? So we know the quantity that maximizes the profit, but what is the actual amount of money that we're taking in? So to find the corresponding profit, we need to take this quantity and plug it back into our profit function. So we take our 220 and we plug it into our profit equation, and we get 4,400 times 220 minus, and then here we have 10 times 220 squared plus 1,400. Okay, if we crunch that number, we get $482,660. So remember, again, this is going to be in dollars. So we were able to find the quantity that maximizes profit and the maximum profit. These are two common questions that come up in this section. So typically what the question will look like is you'll have this setup where you have a cost and revenue equation, and one of these two questions will be the sort of question you are asked to answer. If you are asked this question, what is the maximum profit? You still have to do these steps. You still have to set up the profit equation, find the quantity that maximizes the profit, and then use that to find the actual maximum profit. One of the main things that students get wrong on this type of problem is that they report the quantity when they're asked for the profit. So it's important that you recognize the difference in wording between these two questions. So this one wants the quantity, that's the Q value. This one wants the profit, which means we had to plug the Q value in. So if this was on a mini quiz, this would definitely be one of the solutions, but $220 would probably also be a solution, just to sort of make sure you're reading carefully. So make sure you know what question you are answering if you see this type of problem. Okay, so let's look at the next problem. The next problem is more of a analytical, sort of critical thinking type problem. There's a couple of different concepts wrapped up here that we're trying to reinforce. So let's see if Q represent the cost and R of Q represent the revenue and pi of Q represent the profit of a product with quantity Q. Part A, when profit is maximized, what is the relationship between C prime of Q and R prime of Q? Okay, so think about how we set up profit, how we would think about that in general, how we would solve it in general, and how these might come into play. And then for part B, if marginal cost at 45 units is $57 and marginal revenue at 45 units is 62, approximately how much additional profit is earned by the 46th item? So additional profit is marginal profit. So think about what we know about those definitions and how we might use them to answer part B. Okay, so think about it. I'm going to give about 2 minutes to try to work on these two parts. See if you can sort of reason through what might be true for part A, and then apply what we remember from part 2 to really answer part B. So take about 2 minutes, and then we will go through it together. Okay, take about 30 more seconds. Okay. So we did a problem similar to this back in 2.5, which you may or may not remember, but let's talk about how we might figure out what the relationship is here. So if we're going to talk about maximizing profit, we want to really think about what that means, right? So like profit, we know is revenue minus cost. So this is sort of the generic form. If we were going to try to maximize this equation, we would be looking for critical points. Well, we don't have a representation for R and Q, so the best we can do right now is just set it up as generic derivatives. Okay, so we can do the derivative of each piece because they're separated by subtraction, right? So if things are separated by addition and subtraction, you take the derivative of each piece. Well, if we were looking for critical points, we would want to know when does that equal 0, right? So if we just algebraically manipulate this in terms of what we have here and bring the C prime of Q to the other side, we find that R prime of Q would have to equal C prime of Q to find the critical points. Since there's no other information about endpoints, we know that if we have a function that is maximized, that at that point, R prime of Q is going to equal C prime of Q, right? Just from this sort of thinking about this generally, right? Thinking about in a more higher level conceptual way. One thing we have to be a little bit careful about, however, is if we had really complicated cost and revenue functions, right? We saw a couple when they were nonlinear, but let's say that they're even more complicated and there are many critical points. That also means that there's a possibility that profit is minimized when R prime of Q equals C prime of Q. So the way that we talk about this is in one direction. So profit, when is maximized, will have the property that R prime of Q equals C prime of Q. However, if R prime of Q equals C prime of Q, it doesn't necessarily mean that it's at a maximum. So it's one direction, right? It could be a minimum if there's more than one critical point. So this is a property that we can find by sort of thinking about this in a more generalized way from the top down. So maybe you were able to think about that and figure that out. Maybe you got some parts of that, but hopefully that makes sense now. For part B, we have this idea of marginal cost and revenue at 45 units, and we want to use that to think about the additional profit earned by the 46th item. So when we talk about the additional profit earned by the 46th item, we are talking about the profit that you get from going from 45 to 46, right? And we talked about that with this idea up here with marginals. It's always the additional cost, additional revenue, additional profit by adding one more item. So what we're really looking for here is the marginal profit at a level of 45 units, because that's going to tell us the additional profit from making and selling one more item, which is the same as the profit earned by the 46th item. That's the profit of going from 45 to 46. So we know that marginal profit at 45 will have to equal marginal revenue at 45 minus marginal cost at 45. Okay, that will tell us how much profit we earn going to 46, from 45 to 46. So R prime of 45 is 62. C prime of 45 is 57. We subtract those and we get $5. So the additional profit from making one more item, from going from 45 to 46, will be an additional $5 in profit. And I want to remind you that both profit and marginal profit can be negative. So sometimes when we do this calculation, we get a negative number, and that means that we are losing money by making one more. That's okay too. And the reason I say that is because it's important that we always do revenue minus cost. So sometimes when that comes out negative, students think that they were supposed to flip them, and that's not the case. It's always revenue minus cost or marginal revenue minus marginal cost, depending on what you're calculating. And if it's negative, that just means you're losing money. That's fine too. Okay. So now we're going to sort of introduce a new concept of something that we haven't quite done before. And there is a lot of parts to this problem to sort of walk you through the process of how to complete this. You won't have this many parts to do when you do this on homework. You'll just have to sort of figure out how to set this up. So this breaks it down into the other parts that we need and introduces something called the demand equation. Okay, so we're going to do this in sort of two chunks. We're going to start with part A. So here, a theater has 1,000 seats, and when they set their ticket price at $10 per ticket, the theater sells out. So what that means is if you charge $10 for a ticket, all 1,000 seats are sold. For each additional dollar charged, the number of seats purchased is reduced by 50. So if you charge $11, you only sell 950 seats. Okay. So the first thing we want to do is we want to find the linear equation that will fit this data, right? So what does that mean? We have this point here of 10 and 1,000. Okay. So I'm going to write that up here. And then we also have another point for each additional dollar charged. So that means if we change our 10 to an 11, that's one more dollar, the number of seats purchased is reduced by 50. Okay, so we have 2 points, 2 data points about our situation here. Okay, we want to find a linear equation that fits these 2 points, right? So that means we need to find a slope, we need to find our intercept. Okay, and what we want to do is once we have the equation of our line, we want to use the variables that relate to what we're talking about, right? So instead of x comma y, like we normally would use, we have a price and a quantity. So you have a choice. You can either set up your whole thing doing y equals mx plus b, and once you have your linear equation, change your variables accordingly. Or if you're comfortable with it, you can just start with p's and q's and compute it that way to get your equation. I tend to use x's and y's until I have my final equation, and then I change my variables. And so what we're finding here when you find a line that fits this type of data is called a demand equation. And we'll talk about it once we sort of solve this and what it represents and what it tells us. But for part A, I'd like you to take about 2.5 minutes and find the equation of the line that's going to fit these 2 points. Okay, so try that out, get that set up, and then we'll go through it together in about 2 minutes. Okay, take about 30 more seconds. Okay. So I'm going to start our work down here in the blank space because we're going to build onto it. So I'm just going to copy down our 2 points that we're working with. Now, when we start this, we're looking for the equation of the line that fits these 2 points, right? So what we need is a slope and an intercept to make that work. So our slope here, remember, is going to be the change in y over the change in x. Okay, so I'm going to do everything in terms of x and y and then convert it at the end to p and q. So when we do the change in y, I have 1,000 minus 950 divided by 10 minus 11. And that gives me a slope of negative 50. So the equation of my line starts off as y equals negative 50 x plus b, right? Y equals mx plus b. We need to find our b, so we need to plug in one of our points. Doesn't matter which one you plug in, you're going to get the same solution because it's the same line. I'm going to plug in the first one just because I think the numbers are a little bit easier. So if I plug in that, I'm going to plug in 1,000 for y and 10 for x. So negative 50 times 10 is negative 500. If I add that over, I get b equals 1,500. So now I have y equals negative 50x plus 1,500. So the last step is going to be to convert my variables to the ones that I want to use in terms of economics. So as a reminder, normally we have XY, but this is a price and this is a quantity. So instead of X, I'm going to have P, and instead of Y, I'm going to have Q. So Q equals negative 50P plus 1,500. Okay. And this is an important equation in business because this is called the demand equation, right? If you have a relationship between how much something costs and how many of them you sell, which is what we have here, we get what's called the demand equation. And why this is important is because now we can plug in different prices and find out how many of the tickets we can sell at that price, right? Because they are related. And so the reason we want to do this is because we are going to want to maximize our revenue, right? That's going to be our next step. And if we want to maximize revenue, we need to know the relationship between the price and the quantity. So let's look at the next part of the problem, and then we have to talk about a couple things before we solve. So revenue is represented by price times quantity, where P is price and Q is quantity. Using your equation from part A, I don't know why it said part B, that was a typo. Set up the revenue equation by substituting the demand equation in for Q. We'll talk about that in a second. And then for part C, find the price and quantity that will maximize revenue. So the whole point of this problem is to figure out how to maximize revenue, right? We want to maximize the amount of money that we take in for whatever reason, and this is pretty common when we're thinking about selling things. Now, I want to point out that a lot of people assume that if you fill the theater, that's going to give you the most money, right? So the 10 and the 1,000, but that's not true, right? Because if you charge more money, you don't need to sell as many tickets. And so what ends up happening is you end up with sort of a function that is not quite as obvious as you think it would be. Okay, so we're trying to find a combination of price and quantity that's going to give us the most revenue. That's our ultimate goal. So our first step is to find the demand equation. That's going to be true whenever we're maximizing revenue. And like I said, this is the piece that's kind of new to us. So how do we do that? We're going to take revenue okay, which is price times quantity. And instead of Q, we're going to substitute in negative 50p plus 1500. What that's going to do for us is that's going to give us a revenue equation that only has the variable P in it. So one variable. The reason we need that to happen is so we can take derivatives. We don't yet know how to find derivatives with more than one variable. That's something that happens in Math 128, but we don't know how to do that yet. So when we substitute this into revenue, we want to simplify, and then we can use the derivatives to talk about the price and quantity that will maximize the revenue. When you solve the initial derivative equation, you will find a price that maximizes revenue, and then you can plug it back in here to get the corresponding quantity that pairs with it based on the demand equation. Hopefully that makes sense. So we're going to try this out. I'm going to give you about 3 minutes to try to do parts B and C. So again, you're going to start by setting up your revenue equation, plugging in the demand equation for Q. Then you are going to maximize that equation using derivatives and techniques that we've been practicing in chapter 4. Okay, so take about 3 minutes, try that out, and then we will go through it together. Okay, take about 30 more seconds. Okay. So this is a scenario where price is not fixed, right? So in most other cases we've looked at, we've had one price that we were selling something for, but the price here is changing as well as the quantity. Both of these are changing, which is why we need this demand equation to figure out their relationship. So what we want to do again is we want to plug in for Q what the demand equation is. So minus 50p plus 1500. Okay, what this is doing is this is focusing and fixing revenue to be based on one variable instead of two. So if you have two variables here, which is what's happening in this scenario, we can't solve it yet. We don't have the tools to do multivariable derivatives. But by plugging in this relationship equation, it singles it down to one variable. So I'm going to simplify this by distributing the p through the parentheses. I get negative 50p squared plus 1500p. So now I have a revenue equation that's in terms of one variable, in terms of price. And so that's what I was looking to do in part B. Okay. In part C, I now want to find the price and quantity that will maximize revenue. So again, when I hear the word maximum, I'm thinking critical points. So I want to take the derivative of revenue here. So for the first term, the 2 comes down to multiply the negative 50. So I have negative 100p plus, now the derivative of 1500p is 1500. And I want to know, when does that equal 0, right, to find my critical points. So if I bring this term over and divide, I'm going to get p equals 15. Now remember, P represents price. So this is $15. So that means that my maximum revenue is going to happen when I charge $15 for my ticket. But I also want to know the maximum quantity that goes with it, right? Find the price and quantity that will maximize revenue. So I need to take this 15 and plug it back into the demand equation to find out how many tickets I can sell when I charge $15. Right? So Q equals negative 50 times 15 plus 1500, and I get Q equals 750. So when I charge $15, I can sell 750 tickets, and this is the combination of price and quantity that's going to maximize my revenue. So as I mentioned before, oftentimes people think that when you sell all the tickets, you maximize revenue. But what I want you to notice here is that if you were to charge $10 and sell 1,000 tickets, that would get you $10,000 in revenue, right? Price times quantity. But here, if we multiply the price times quantity, we get 15 times 750, we get $11,250. So that is the revenue, that is the maximum revenue you can obtain given these conditions, right? So when we do this particular problem, right, what does it look like in context? So you have this setup, you have a theater that has 1,000 seats, or, a baseball stadium sells out 1,000 seats, or, some other similar type of thing. And we have a relationship between how much we can charge and how many things we're selling, right? So we have some setup here, and then the question will be something like, find the price that maximizes revenue, find the quantity that maximizes revenue, or find the maximum revenue. So all of those things come from finding the demand equation, now setting up your new revenue equation, finding critical points, and then finding the appropriate final answer. Right? So we found all three. We found price, quantity, and revenue. We could ask you for any one of these three things, but the top part stays the same. We still have to find the demand equation, the revenue equation, we have to do derivatives, but then we have to know which one of these final numbers we're looking for. So just make sure that you read the problem carefully so you know which number we're actually looking for in the context of the problem. Okay, so like I said, this is a pretty common problem. I think there's one on homework, and it wouldn't be unusual for you to possibly have one of these either on a mini quiz or a chapter quiz. They are a little bit longer, so you would not have more than one on a chapter quiz, but you definitely could have one. Okay, or we could definitely just ask you about the demand equation, which takes a little less time just to find that first part. So as I mentioned at the beginning of class, today is an abbreviated lecture just because you do need time to go back to the other sections. So we're going to stop here for today. I strongly encourage you to work on this homework sooner rather than later so that if you do have to go back and reference or review other stuff from the other 2 economic chapters we did, that you have time to do that and to ask questions at Drop in Help if you need it. Okay. Otherwise, have a good rest of your day, and I will see you guys on Thursday.